the big issue is that you load up hemoglobin with oxygen in the lungs, and you move it around the body, and it comes to a muscle that's working hard and needs oxygen, and hemoglobin has to release the oxygen. So how does that happen? And that's largely what I'm going to be talking about today. How does the hemoglobin release its oxygen to the tissues that need it? What are the factors that promote that happening? And also, of course, at the same time, pick up carbon dioxide. So that's what this says here. This is where we finished last time, if I recall. The binding of oxygen to hemoglobin in the lungs is rapid at normal alveolar pO2. The release of oxygen to the tissues depends on the conditions in the tissues. So the conditions in the lungs are high pO2 in the alveoli, low pO2 in the blood. Oxygen diffuses into the blood and then binds to hemoglobin. But what about the reverse situation? It's more complex, and I think it's cool. It's really good physiology. So what it does is it varies with the conditions in the tissues where it finds itself. In the working muscles, for example, and the other tissues, but the working muscles is a good example of muscles that require a lot of oxygen. In working muscles, the blood is going to find different conditions. It's going to find different conditions of oxygen. It's going to be low. It's going to find different conditions of pH, because there's a lot of carbon dioxide there. Remember the relationship between carbon dioxide and pH. And it's going to find a different temperature, because the temperature in working muscles is going to be higher. And all of these things promote hemoglobin dropping it off its oxygen there. And we're going to have a look at that now. And we show these relationships in what's called dissociation curves. So this is a hemoglobin oxygen dissociation curve. So look at this graph here. Vertical axis is the percent oxygen saturation of hemoglobin. Do you remember from last time? Fully saturated blood, the hemoglobin was, what, 98.5% saturated. So this is the PO2 here. The PO2 in the lungs is about 100 millimeters of mercury, and so at 100 millimeters of mercury in the lungs, the hemoglobin is 98.5% saturated. So it doesn't quite meet the dotted line of 100. So that's the fully saturated hemoglobin here. The hemoglobin, the oxygen, partial pressure of oxygen in the tissues, if you remember, is about 40 millimeters of mercury. So that's here. And at 40 millimeters of mercury, do you remember what the saturation of hemoglobin was? About 75%. So that's the normal physiological range of PO2s, and the normal physiological range in the saturation of hemoglobin is about between 75% and 98.5%. So this here is the physiological range of the oxygen hemoglobin dissociation curve. If you want to take it further in a test tube, you can get this part of the curve as well, but this is the physiological range within the blue dotted box. And so look at the shape of the curve. It's S-shaped, and that has some significance because, look here, at atmospheric pressure, which can vary, and would vary slightly the PO2 in the arterial blood, with small changes of PO2 here, there's very little change in the saturation of hemoglobin. Well, that's good, isn't it? Because if you go to the mountains where the elevation is high, there's a little bit less oxygen in the atmosphere, it's not going to affect you very much. But as soon as you get down in these regions of PO2 down here, which is what hemoglobin finds in the tissues, then rapidly it unloads its oxygen. So that's good. So down here at 40, between say 40 and 60 millimeters of mercury oxygen, then it it unloads its oxygen into the tissues. So that's called a hemoglobin-oxygen dissociation curve. Curve is S-shaped. This is so that it doesn't vary very much with small changes of oxygen saturation of hemoglobin, and this steeper part of the curve is important so that the oxygen is unloaded from hemoglobin very rapidly when it gets into the tissues where it's needed. So I think that, is there any questions on that? Pretty straightforward, I guess. So we need to look at this okay, so look, here's what's going on. Here is the, this is oxygen exchange in the tissues. So the oxygen is coming in oxygenated, 100 millimeters of mercury, reaches the tissues at about 40, and the oxygen then unloads from the hemoglobin. Here it is, oxyhemoglobin. The oxygen unloads, diffuses into the plasma, and from there into the cell, and the blood leaves deoxygenated at about 40. So that's straightforward. So let's go back to the oxygen hemoglobin dissociation curve and look at what happens in order to change the affinity of hemoglobin for oxygen. So look here, the affinity may change under different conditions, and these changes change the rate of delivery of oxygen to the tissues, the unloading of oxygen from hemoglobin. So look over here. If we shift, there's the normal curve there. If we shift this curve to the right, here, rightward shift, that corresponds to a decreased affinity of hemoglobin for oxygen. So look, in the normal curve, you get 80% saturation at about 45 millimeters of mercury. In the rightward shift, you get 80% saturation at more like 55 millimeters of mercury. So you need 55 millimeters of mercury to get the same saturation as the normal curve. In other words, the hemoglobin now has decreased affinity for oxygen. You need more oxygen in order to get the same saturation. Shifting the curve to the left is an indication of increased affinity. So for 80% saturation here, you only need 40 millimeters of mercury. Can you see what's going on here? For 80% saturation, 40 millimeters, 45 or 50, 45, and 55. So the shifting the curve left or right is an indication that the hemoglobin's affinity for oxygen is changing. Well, that's significant, that's important, because in the tissues where you want the hemoglobin to unload its oxygen, would be very nice if you could decrease the affinity of hemoglobin for oxygen. And then the hemoglobin would release its oxygen where you need it. And bingo, guess what? That's what happens. So the next picture shows you the practical application of this under two different conditions. So here is the oxygen, the normal oxygen hemoglobin dissociation curve at 37 degrees centigrade, which is what it is in most parts of the body. And then when the blood reaches the working muscles, because of the metabolism going on in the working muscles, the temperature is going to be higher. Look what happens to the hemoglobin oxygen dissociation curve when it finds itself in warmer conditions over here. The hemoglobin oxygen relationship, there's decreased affinity of hemoglobin for oxygen. So the oxygen then is released more easily. So increased temperature in the tissues due to higher metabolism favors the release of oxygen, the rightward shift. Just what you want in the tissues. Terrific, perfect. Look what else it finds in the tissues. If you decrease the pH from the normal pH 7.4 towards a lower pH of say 7.2, you also decrease the affinity. Guess what hemoglobin finds in working muscle? Increased CO2 in the working muscle, or in the tissues generally, lowers the pH. This causes a rightward shift in the dissociation curve. Hemoglobin gives up its oxygen in the tissues. Perfect. So the conditions in the tissues favor the release of oxygen from hemoglobin. Exactly what you want in the tissues. And this terrific piece of physiology is known as the Bohr effect, named after a physiologist called Bohr. So that's and that is very significant. So these are two of the conditions in the tissues which favor the delivery of oxygen from hemoglobin. Yes.
If it's lactic acid being released in the muscles instead of carbon dioxide, is it still the Bohr effect?
Yes, and I'll come to that point in a few slides' time. Okay? Good question. The bottom line is, hemoglobin doesn't care how the pH is lowered. It's lowering of the pH that counts. So whether it's lactic acid or whether it's carbon dioxide, it's the same effect. And it's shown on a later slide. I'll point it out when we get to it. So the amount of CO2 in the blood controls acid-base balance. I've already stressed that, haven't I? And Dr. Alexander's going to come in a few weeks to talk about that. So carbon dioxide, and I think I made this point last time. Forgive me if I did, but it bears repeating. Carbon dioxide is carried in 3 different places in the blood. 1, a small amount is dissolved in the plasma, from where it diffuses very rapidly. Most of it is carried as bicarbonate ions due to the effect of carbonic anhydrase in the RBCs, and we've talked about that. Show you again in a minute. And finally, a small amount binds to hemoglobin as carbaminohemoglobin. Talked about that last time too. So 3 places that carbon dioxide is carried. By far, the most important one is as bicarbonate ion. So here's just a table, I don't need to remember the numbers, but it illustrates what I just said, that if you look at the percentage of total CO2 in the blood, 90% of it is dissolved as bicarbonate. 5.5% roughly, depending on whether you're talking about venous or arterial blood. About 5.5% is dissolved, and about 5% is bound to hemoglobin. There's a small but significant difference in the amount bound to hemoglobin in arterial blood compared to venous blood. Can you see that? 5 goes up to 7. Let's just have a look at that. So I'm not minimizing the effect of bicarbonate. This picture shows that by far the most is carried as bicarbonate. But some is carried bound to hemoglobin as carbaminohemoglobin. Now, just as here, the loading of oxygen and unloading of oxygen from hemoglobin depends on the conditions, so it turns out that the same thing can be said for the loading of carbon dioxide onto hemoglobin. Now, it's not nearly as important as this, because huge amounts of oxygen are bound to hemoglobin, and only small amounts of carbon dioxide are bound to hemoglobin. And so physiologically, significance-wise, this one is way more important than this one, which is the same effect showing carbon dioxide binding to hemoglobin. So here is the total blood carbon dioxide. Here is the PCO2. And look at the binding curve for CO2 under different conditions. So if you had a situation where there was 0 millimeters of mercury, you never get that, of course, physiologically. PO2 0. The total blood carbon dioxide is up here, whatever that number is. As you raise the oxygen concentration in the blood, so the affinity of hemoglobin for carbon dioxide goes down. Look, goes down. When it from physiologically, this would go from 40 to 100. But in fact, and that would just give you a small drop here. What this shows you is an experimental situation, showing you that as you raise the oxygen concentration in the blood, the affinity of the hemoglobin for carbon dioxide goes down. So the dissociation curve for carbon dioxide varies under different conditions of oxygenation. It's different for oxygenated blood and for reduced blood. And as the oxygen increases, for example in the lungs, carbon dioxide is released. Just what you want. So to some extent, the same reasoning goes for carbon dioxide as it does for oxygen. Oxygen in the tissues finds conditions where the hemoglobin releases it. The hemoglobin in the lungs finds conditions where carbon dioxide can be released. Just what you want. And this is called the Haldane effect. And it's not nearly as important as the Bohr effect because way more oxygen is carried than carbon dioxide is carried. But the same kinds of concept applies to both of these things. Is that clear? I haven't quite finished with this. I've got a picture which tries to put this together and make sense. But it does make sense, generally. So here is a carbon dioxide exchange in the tissues, and we've been here before. So the blood is coming into the tissues with 40 millimeters of mercury carbon dioxide, and it finds 46 millimeters of mercury carbon dioxide in the tissues, and the carbon dioxide then is, here it is in the tissues. The carbon dioxide diffuses very easily into the plasma, and from there the carbon dioxide goes into the red blood cells. Some of it, most of it, combines with water. Under the influence of carbonic anhydrase forms carbonic acid. Carbonic acid very rapidly dissociates into bicarbonate ions and hydrogen ions, and the bicarbonate ions are pumped. And as we saw last time, there's a pump which pumps bicarbonate out, and there's a pump which pumps bicarbonate in. And there's a few professors upstairs that love the bicarbonate pump and the different directions, and we don't need to go there. But there's cell physiologists and so biochemists who work on this bicarbonate pump. And it's incredibly important, it turns out, because of effects on pH and on respiration. So this bicarbonate pump is an important one. I'm not going to say any more about it, but I suspect that Dr. Alexander will. Anyway, so here the carbon dioxide, it goes in and goes through this bicarbonate reaction here, and look, a little bit of it here binds to the CO2 as carbamino hemoglobin that we've talked about. And then the blood leaves, having loaded up with carbon dioxide, the blood leaves from 40, blood leaves the tissues at about 46. So we've looked at that before, and that's what's going on with carbon dioxide. Now, these next two pictures are meant to put together three different things. Let's go to the lungs. What this picture does is, and you can sit at home and you can work through it, and it makes sense and it puts together what I've talked about. We're in the lungs where CO2 is unloading and oxygen is loading onto the hemoglobin. So in the lungs, the hemoglobin finds high PO2 and and low carbon dioxide. And via a series of reactions, all of which we've talked about all of these, the net result is that hemoglobin's affinity for oxygen goes up and oxygen is loaded. So if you take this picture apart, you'll find the lower CO2 in the blood causes a lower hydrogen ion concentration, the pH goes up. Via the Bohr effect, hemoglobin's affinity goes up. We talked about this just now, the shifting of the curve due to pH. Also, the CO2 in the blood has a direct effect on hemoglobin, causing carbon dioxide to unload. Via the carbamino effect, hemoglobin's affinity for oxygen goes up and oxygen loading goes up. The higher oxygen in the blood here via the Haldane effect causes carbon dioxide unloading, and then the carbamino effect causes oxygen loading. So here's the Bohr effect, the Haldane effect, and the carbamino effect. All three conspiring in the lungs to load hemoglobin with oxygen. This just puts together the three conditions of pH, carbon dioxide, and oxygen that I've talked about in the previous pictures. In the same way, in the tissues, what do we find in the tissues? We find low oxygen, we find high carbon dioxide. And this picture shows you carbon dioxide loading onto hemoglobin in the tissues, which is what you want, and oxygen unloading from the hemoglobin in the tissues, which is what you want. So here in the tissues, the high PCO2 causes a higher hydrogen ion concentration, so it's more acid. Via the Bohr effect, hemoglobin's affinity for oxygen goes down, and the oxygen's unloaded. This is what we talked about with the Bohr effect here, the effect of pH on hemoglobin's affinity for oxygen. There's also a direct effect via the carbamino effect, which lowers the hemoglobin's affinity for oxygen and causes oxygen unloading. The low oxygen PO2 via the Haldane effect also causes oxygen unloading. So you can have a look at this at home and try and put together the conditions that I've talked about, Bohr, Haldane, and carbamino, and see how these all work together to affect the loading and the unloading of oxygen and carbon dioxide from hemoglobin. And like all important physiological effects, there's multiple inputs. And after you've discussed it all, you hope you can come up with a picture as clear as this, which tries to put it all together and make sense of it. Bit blown away by that, or is that a stunned looks over here? Eye rolling going on? Okay. Well, good luck with that. It does make sense. It's all good. It's all good stuff. Read it, follow, look at the notes, read your textbook, give me an email if you want to discuss it further. So as far as I'm concerned, this is the good physiology part. And sometimes when I talk about this, a hand goes up. And they say, over in biology we did this or something like that. And they talked about diphosphoglycerate. Does this ring a bell with people? No?
Yeah, biochemistry.
Biochemistry talks about it, do they? Right, well, I used to forget about this because it's relatively insignificant. It doesn't really fit with what we talked about. But then I thought, oh, damn it, someone's going to put their hand up and ask about this. So I put this slide in here just so that this fits with what biochemistry, it turns out the biochemistry talks about. There is another substance called, which affects the oxygen dissociation curve. It's called diphosphoglycerate, DPG. present in red blood cells and tissues, and it decreases the oxygen affinity for hemoglobin. So it's exactly what we've been talking about. Yet another factor which affects the oxygen affinity of hemoglobin. And so this substance, DPG, is increased in tissues under conditions of hypoxia, thus increasing oxygen delivery to the tissues that really need it. I really don't know what the biochemists talk about with DPG, but if you're if you're doing biochemistry and this comes up, you can see how it fits into the Bohr effect, which is the really good one. Okay, carbon monoxide. Come across that? What's that all about? Well, about 6 months ago, I had my furnaces serviced at home, and the guy said they were fine, and where's my carbon monoxide monitor? I said, well, I don't have one. And he said, well, every home will have a carbon monoxide monitor, because he was selling them, of course, you know. So I didn't buy one from him. I went down Home Depot and bought one at half the price. But I did put one in. Carbon monoxide is a product of combustion. And so when your furnace is burning, if it doesn't burn efficiently, you get carbon monoxide released into the house. That's not good news. When your car is running and burning gasoline, carbon monoxide is in the exhaust. And you maybe have heard of people who, one of the favorite painless methods of suicide is to sit in a car and run a tube from the exhaust pipe into the car and close the windows, and you go to sleep and you don't wake up again. So carbon monoxide poisoning is a significant issue. And the reason that it's such an issue is that carbon monoxide, produced commonly by combustion, and everyone really ought, now I've got one, everyone ought to have a carbon monoxide monitor in their home. You can get them fairly cheaply at Home Depot. They just plug into the wall and it tells you what the carbon monoxide level is in the air in your bedroom. And it should be 0. And so the issue with carbon monoxide is that it's colorless. It doesn't have any smell, doesn't have any taste, you can't see it, you just don't know. What it does is, it binds to hemoglobin at the same site that oxygen binds, but it binds 200 to 250 times more efficiently than oxygen does. And, not only that, but it doesn't come off. So it's not governed by these issues of hemoglobin efficiency for oxygen. Carbon monoxide, once it's bound, it stays bound. And it's so much more efficient than oxygen that it displaces oxygen from hemoglobin. And when the carbon monoxide combines with hemoglobin at the same site on the ion as oxygen, it forms a compound called carboxyhemoglobin. Uh-oh. Carboxyhemoglobin. Carbaminohemoglobin. Don't get those mixed up. Carbaminohemoglobin, good. Carboxyhemoglobin, bad. So it binds very avidly to hemoglobin and it doesn't come off again. And so the oxygen carrying capacity of the hemoglobin goes down, and you don't get oxygen delivered to the tissues, and you die. So a very dangerous substance. It shifts the oxygen dissociation curve to the left, increasing oxygen delivery to the tissues. It does not affect dissolved oxygen. And here's an issue which leads into the next class. Because it only affects the oxygen that's bound to hemoglobin. You have the same amount dissolved in the blood. And what this means is that when you're being gradually poisoned by carbon monoxide, you don't breathe more heavily. you just breathe normally and you drift off to sleep. Normally, when the oxygen levels in your blood go down, you start to breathe more rapidly. But this doesn't happen with carbon monoxide poisoning, and the reason for that is that it doesn't affect the dissolved oxygen in the blood, only the oxygen bound in hemoglobin. And it is the dissolved oxygen that causes you to breathe more heavily when you are normally lacking oxygen. Doesn't happen with carbon monoxide poisoning. So why does dissolved oxygen make you, if lower dissolved oxygen make you breathe more rapidly? We'll find out on Monday. Have a good week.
He did let us off.